Assalamu alaikum to one and all. It's great to have you back to Sir K Loves Physics and Chemistry tutorials for high school students. Today's episode tackles a quite challenging problem on projectile motion. So stick around till the end of this video. Watch and learn. The question is, a physics professor did Daredevil stunts in his spare time. His last stunt was an attempt to jump across a river on a motorcycle. The takeoff ramp was inclined 53.0 degrees. The river was 40.0 meter wide and the power bank was 15.0 meter lower than the top of the ramp. The river itself was 100 meters below the ramp. You can ignore effects of air resistance. And the questions are, letter A, what should his speed have been at the top of the ramp to have just made it to the edge of the power bank? Letter B, if his speed was only half of the value found in part A, where did he land? Let acceleration due to gravity g equal to negative 9.8 meters per second squared. As shown in this sketch, the initial velocity v0, the cyclist treated here as a particle, has an angle of projection theta equal to 53.0 degrees above the x-axis or the horizontal. The river has a width denoted by small letter d equal to 40.0 meters. The edge of the far bank is 15.0 meters lower than the top of the ramp. And our target variables are letter E, the speed v0 of the cyclist at the top of the ramp to have just made it to the edge of the power bank. And letter B, the landing point of the cyclist if his speed was only half of the value found in part A. Moving on to our computations, we first express the x and the y components of v0. The x component v0 x is just equal to v0 multiplied by cosine of the angle 53.0 degrees, or that is v0 x equals 0.602 times v0, and its y component v0 y is just equal to the product of v0 and the sine value of 53.0 degrees, right? Which is equal to v0 y equals 0.799 times v0. The horizontal displacement delta x, which is given as the width of the river denoted by small letter d equal to 40.0 meters, right? That is equal to the product of v naught x and the time t, or delta x, which is 40.0 meters, equals v naught x times the time t. All right, the time t here is how long it would take the cyclist to have made it to the edge of the power bank, right? So the delta x of 40.0 meters is equated now to our expression for v naught x, which is 0.602 times v naught, and that is multiplied by the time small letter t. So isolating v naught, we'll have our equation for v naught, that is v naught is equal to 66.4 meters divided by the time t, and we label it here as our equation number 1. All right, take note, in equation number 1 we have two variables or unknown variables, the initial speed v naught as well as the time t. So we need to have another equation. All right, the second equation is based on the fact that the delta y, or the displacement of the cyclist after a time t, all right, is just equal to the product of the b naught y, which is already expressed as 0.799 v naught, multiplied by the time t, all right, plus 1/2 gt squared. But we already simplified 1/2 of the acceleration due to gravity, all right, where g is considered negative. So our equation number 2, therefore, okay, is given here as negative 15.0 meters. This is the y displacement of the cyclist after time t, equated to 0.799 v naught t minus 4.9 t squared. So we label it here as our equation number 2. With two unknown variables, right, and with two equations, independent equations, we will be able to determine each of these unknown variable coming up very soon. All right, so to continue with our computation, so earlier we came up with this equation labeled as equation number 2. Negative 15.0 equals 0.799 v naught times t minus 4.9 t squared. We can simplify this equation number 2, all right, and get t squared minus 0.16 v naught times t minus 3.1 equals 0, right? And isolating v naught, we will get v naught equals quantity t squared minus 3.1 all over 0.16 times the time t. And combining this simplified equation number 2 with equation number 1, v naught equals 66.4 meters divided by the time t. So with this simplified equation number 2 combined with equation number 1, this is what we will get. Quantity t squared minus 3.1 divided by 0.16 times small letter t equal to 66.4 divided by the time t. right? So you will notice that the uh, the left term has its denominator 0.160, which when cross multiplied, all right, to the other side of the equation, this is what we will get. Quantity t squared minus 3.1 equals 0.160 times 66.4 over the time t, right? And obviously, uh, the variable t, small t, cancels out, and we will uh, have this reduced equation. T squared minus 3.1 equals 10.6. 10.6 is the result of multiplying 0.16 by 66.4. All right? So from here, we can now determine the value of t. But first, we will have to transfer 3.1 to the other side of the equation, and we will come up with the value of t. All right? After adding 10.6 plus 3.1 and getting the square root, all right, of their sum, we will get the value for the time t equals 3.7 seconds in two significant figures. Finally, from equation number 1, all right, v naught equals 66.4 meters divided by the time t, all right, we can proceed and determine the value of v naught. All right, so we just divide 66.4 meters by the computed time t of 3.7 seconds, and our final answer for v naught equals 18 meters per second in two significant figures. For our solution to question letter B, where the landing point of the cyclist is if his initial speed is half of the initial speed v naught obtained in part A, right? That is, if his initial speed is equal to 9.0 meters per second, but with the same angle of projection theta equals 53.0 degrees. So, just like in part A, all right, uh, we determine the x component labeled as b naught x, which is just the product of uh, v naught 9.0 meters per second and the cosine value of the angle 53.0 degrees, right? So when we do our math, that's equal to 5.4 meters per second. And for the y component, b naught y, okay, that's equal to 9.0 meter per second times the sine value of 53.0 degrees, or that is 7.2 meters per second. Again, we use the equation for the vertical displacement delta y, right, in determining the time t, because delta y is given as the distance between the top of the ramp, all right, to the surface of the water in the river. That is equal to 100 meters. But since we are talking about displacement relative to the top of the ramp, we label delta y as negative 100 meters all right? Because that is 100 meters below the top of the ramp considered as a reference. And that's equated to um, the product of the vertical component b naught y, all right, which is equal to 7.2 meters per second, and the time t. So our target variable here is the time t, defined here as the time for the cyclist, all right, to land um, we are predicting that because of the smaller value of the speed that the cyclist will have to take, all right, we are predicting that the cyclist will land on the surface of the water in the river. So the time here is how long it will take for the cyclist to hit the water in the river. All right. So our complete equation for delta y is negative 100 meters equal to 7.2 t minus 4.9 t squared. All right. Minus because we consider the acceleration due to gravity to be negative. And 1/2 of negative 9.8, of course, is negative 4.9. All right, so once again, the delta y, all right, or the displacement of the cyclist after a time t is expressed in this equation. Negative 100 meters equals positive 7.2 times t minus 4.9 t squared. All right? And when you simplify this, okay, we will actually get a quadratic equation. All right? A quadratic equation uh, simplified as t squared minus 1.5t minus 20.4 equals 0. Right? So how we came up with this? We actually just transferred 4.9 or negative 4.9 t squared to the left side of the equation, and then uh, we did that also to 7.2 times t. So both of these terms, okay, are transferred to the left side of the equation, and then divide the whole thing by 4.9, right? We want the numerical coefficient of t squared to be just equal to 1, right? So when we divided 7.2 by 4.9, what we got is negative 1.5t. And in the case of 100 divided by, or negative 100 divided by 4.9, we got 20 or minus 20.4, all right? So all of this are equated to 0. This is our simplified quadratic equation. So using the quadratic formula, we can determine the value of the time t, right? So uh, according to the quadratic equation formula, okay, the value of the time t is equal to the negative 1.5, okay? In this quadratic equation, negative 1.5 is called the what we call the B coefficient. So the B coefficient is written here as negative 1.5. And then plus minus the square root of the square of the b coefficient, which is negative 1.5, that has to be squared, and then minus 4 times the product of the numerical coefficient of t squared, that's referring to the coefficient a, all right, which is understood to be 1, and then multiplied also by the what we call the c term, all right, which is negative 20.4. And since originally our operation is minus 4ac, and that 20.4 is supposed to be negative, so we will have a double negative. That's why we get here a positive sign. So inside the radical sign, we have the terms the square of negative 1.5 plus 4 multiplied by 20.4, right? And the whole of this, all right, all the terms inside the bracket is to be divided by 2 times the numerical coefficient of a, which is understood to be 1. So that's just divided by 2. And simplifying, all right, this is what we will get. Negative 1.5 plus minus, after getting the square and multiplying 4 by 20.4, what we get now is positive 2.25 plus 81.6, right? So the sum of these two numbers will be or are inside the radical sign, so we will get the square root of their sum, right? Which in fact is equal to negative 1.5 plus minus 9.2, right? 9.2 is the result of getting the square root of the quantity inside the radical sign. So now notice that we have two operations, plus minus, or negative 1.5 plus minus 9.2 before we divide the result by 2. All right. If we take the negative sign of 9.2, then we will end up getting a negative time, right? Which is meaningless in this problem situation. So we just choose the positive value of 9.2, right? In other words, negative 1.5 plus 9.2 and then divide by 2, we will get, all right, the value for the time t equals 3.9 seconds in two significant figures, right? So this is the time that it takes the cyclist, okay, to land on the surface of water, okay, with that given speed, half of the original speed, okay, obtained in part A, right? So from here, in just a little while, we will proceed in determining the exact point or landing point of the cyclist, right? How far it is from the first bank or from the far bank. All right, we can compute the delta x or the point where the landing of the cyclist is. Okay, and this is determined by just using the formula delta x equals b naught x. All right, this is the x component of the initial speed b naught multiplied by the time t, since we already have the value for the time t, 3.9 seconds. Right? Substituting, we get 5.4 meters per second times 3.9 seconds. And we will get the value of delta x equal to 21 meters. So delta x means the horizontal displacement of the cyclist upon hitting the water, all right, from the first bank, all right, 21 meters from the first bank. Therefore, we can describe our final answer that the cyclist, in fact, lands on the water 21 meters from the near bank, or that is 19 meters from the far bank, since the width of the river is 40.0 meters. All right. So 40.0 meters minus 21 meters, we also get 19 meters if what we want is relative to the far bank. Okay, the landing point would be 19 meters. Right? So that's it. We are done. Till the next episode, mabuhay. Masya Allah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.